Oh, hey there. How's it going? My name is Ryan, and you're on day 7 of Advent of Code and Elm. I always have a weird intro in the beginning, so just get used to it. So far we have done 6 Advent of Code problems. If you haven't seen the playlist, it should be in the description below. But today we're going to work on problem number 7. And that's if my page loads when I click the Advent of Code button. Nothing like a live demo to really slow things down. But just so you know, what we've been doing so far is we have been doing all of these problems in the web browser. I just cleared out yesterday's solution. And now we're on day 7, part 1. Is this the AWS thing that happened today? There was an East Coast AWS downage earlier, and I was like, is Advent of Code affected? But looks like it isn't. How this usually works is I will click this problem. I haven't seen it before. And what we're going to do is we're going to work through how we can do it together. I'm using Ellie, which is a way for me to do Elm in the browser without having to install anything. And Elm is just a programming language that compiles to JavaScript that I really like. And that's what we've been using for the entire series. So let's get started and check out day number 7. See what our elves are up to. Last time we left off, they were looking for keys in the bottom of the ocean. So each puzzle's had something to do with a submarine or an ocean. So just a heads up in case the intro text is a little bit weird here. It is weird. A giant whale has decided your submarine is its next meal, and it's much faster than you are. There's nowhere to run. Suddenly a swarm of crabs, each in its own tiny submarine, it's too deep for them otherwise, zooms in to rescue you. They seem to be preparing to blast a hole in the ocean floor. Sensors indicate a massive underground cave system just beyond where they're aiming. The crab marines all need to be aligned before they'll have enough power to blast a large enough hole for your submarine to get through. However, it doesn't look like they'll be aligned before the whale catches you. Maybe you can help. There's one major catch. Crab submarines can only move horizontally. You quickly make a list of the horizontal position of each crab, your puzzle input. Crab submarines have limited fuel, so you need to find a way to make all of their horizontal positions match while requiring them to spend as little fuel as possible. For example, consider the following horizontal positions. So this is a list of positions here. This means that there's a crab in the horizontal position 16, a crab with the horizontal position 1, and so on. Each change of one step in horizontal position of a single crab costs 1 fuel. You could choose any horizontal position to align them all on, but the one that costs the least fuel is horizontal position 2. So it's saying from 16 to 2, that'll be 14, from 1 to 2, that'll be 1. And basically when you sum all those up, it's going to cost a total of 37 fuel. This is the cheapest possible outcome. More expensive outcomes include aligning at position 1, which takes 41 fuel, position 3, 39 fuel, or position 10, which takes 71 fuel. So determine the horizontal position that the crabs can align to using the least fuel possible. How much fuel must they spend to align to that position? And so since I have an account, I just signed in with my GitHub here. I'm going to have a different puzzle input than you might have if you go to Advent of Code and try this yourself. But what we're all going to have in common is this problem and this test input. So let's copy this, move over to Ellie, and start seeing this in the browser. Okay, cool. So we start this by just getting the raw string input, and then I'm calling string.trim on this. And basically it's taking that string and it's just getting rid of the new lines. We used this in previous videos. And what I want to do next is I'm going to split my string on commas, and that'll give me a list of strings. And now that I have a list of strings, I'm going to use list.filterMap, which is a function we've used previously to turn strings into integers. So because that operation can fail, we're going to use filterMap, which takes care of like the just stuff that you see here, because Elm uses maybes to deal with possible failures. Okay, so we have our positions. These are our starting positions, so I'm just going to move this into its own function. Starting positions. And this is going to be a list of ints. Oops. So here I'm just adding a type annotation at the top so we can have some compiler help in case something's wrong. All right, cool. So we have our starting positions. And now what would be nice to know is for each like position, like how much fuel would be needed to get there. So what I'm going to do is I'm going to start by finding the farthest position. So like 16 is like the biggest, and the least like the smallest position. So the max and min of this list. And what I think that'll do is like give us bounds for our math and try to figure out like what between that like range of numbers, what's going to be optimal. So we're just going to kind of brute force it for now and see if that works for our actual puzzle input. So I'm going to say, I'm going to make a function called with, min, and max. And what with, min, and max is going to do is it's going to take in our list of numbers as we have them, and it's going to return the minimum number. And we can have that be a maybe. I'm gonna assume that the list isn't empty, and then this is going to be our initial list. So this is going to be like our crabs, which is a list of integers. So basically, we're going to take each one of these. Oh, is that big enough to see? Yeah, I think it is. Okay. We're going to take each of these one at a time, and we're going to kind of append on the maximum and the minimum number. So I guess what we can do is we can return a maybe on the outside. And so what you'll see here is this is going to be all of our crabs. And if we have no crabs, then we're going to not be able to find a min and a max. So we're just going to fail with a nothing. But if we do have at least like the first crab, and then some more, what we can kind of guarantee that we'll always have a number to put in min or max. So this is a way to deal with like, what if we got an empty list? How do we get the min and the max of an empty list? So what we're going to do is we're going to say the minimum is going to be list.minimum. I think that's a function. And we're going to give it crabs, and I think list.minimum. Yeah, list.minimum is going to take a list, and if there's numbers in the list, it's going to give us the smallest one. If not, it's going to give us nothing. So what we're going to do is we're going to do that, and then if for some reason that fails, which we kind of know it won't, we're just going to fall back to the first item in the list. And that'll take care of our maybe problem. So maximum crabs, such a weird phrase, maybe with default first, and then we're going to take our list of crabs and return it. So hopefully we'll see the min, the max, and the list of crabs get printed here on the right when we hit compile. And it looks like I've done something wrong. Oh, that's right. So for this whole thing, we're going to wrap that in adjust because we want to return a maybe record. Let me indent this and use some L format. Okay, cool. So what we're seeing here is we've got our maximum of 16 and our minimum of 0. So we can use that to kind of get like an upper and like a lower bound for our range. So what I'm going to do is make another function and say we're gonna make a range from 0 to 16, and then for each one we're going to calculate the fuel cost of each crab. So I think we can just loop through each of those, and then we'll have all the fuel costs associated with each number. So I'm going to make a function called toFuelCosts. And so toFuelCosts is going to take in what we left off with. I'm going to do a maybe.map here, and that's going to handle the nothing case. It's going to like ignore it. And what we're going to do is we're going to take in this, and we're going to return. It's going to be a dictionary, which is going to like have a position, and it's going to say like what are the. We're going to have like a list of all the costs like for each crab. So position and cost are just aliases for integers. So I like to use these to make the code a little bit easier to read, and make it easier for us to remember what we're storing in each spot. When everything's integer, it kind of gets confusing. So that's what we're going to do here. And then this is going to be our data that we had before. And then what we can do is, for now, I'm going to import dict. So dict is a module that's available in the Elm core library, and it allows you to associate keys with values. We've used it on previous problems, and it's a good way to like be able to look something up really quick. So what I want to do is I want to say, I'm going to make a dict from a list, And so what we can start with, so let me just start by saying it'll just be an empty list, and then you'll see that we have an empty list, and then because of the maybes, it's wrapped in a just. I'm going to comment this out for a second, and we're going to walk step through how we can build up this dictionary and see where these costs, how to get these costs rendering on the screen. So this just comments out the header, so I can compile. And what we're going to start with is we're going to start with the range of numbers. So we're going to start from the minimum number. We're going to go to the maximum number. And what this does is this enumerates everything from 0 to 16, including 0 and 16. So we're going to start with that. And then what we're going to do is we are going to map through each one of these numbers. So with each one of these numbers, we're going to be able to, I don't even know if we're going to use a dictionary at the end of this. So what we're going to do is we're going to find the cost of movement. So finding the cost of movement is just going to be another function. And this one is going to take in a number like 0, 1, or 2. So it's going to take in a number. And we're also going to pass it the crab list that we had before. So we're going to pass that in first. And what we're going to do is we're going to return basically a pair. So this is going to be the, well, I guess position. We should start using our type aliases. Yep. And then we're going to say, I'm going to add crab as an alias here. So that's a list of crabs. Position. These are all just integers, so they're totally interchangeable. But I think it might be nice for understanding like what these values represent in our code. So we're going to have a list of costs here. So the goal of this function is going to be taking those crabs, the positions of those crabs, and we're going to take a position that they need to move to. So I'm going to call this like the target position. And what we want to do is we're going to loop through each one of these. And so we'll return the target position here. And then what we're going to do is we're going to loop through each crab. And we're going to get the difference, like the difference between the crab's position and the target position. And we're going to use absolute value, so that's always a positive number. We don't want to deal with like the crab was at 5, and then we're trying to get to position 10, and then we end up with like a distance of -5. That wouldn't be any good. So what we're doing here is we're using list.map. I could put it at the end here, or we could use the pipeline syntax that we've been using. Whatever your preference is, you can use that. And basically what this is going to do is this is getting the movement cost for each position in the list. So what we end up with at the end is the ability to basically map through the second value in our tuple and then like sum up the list. So what this is doing is this is going through each number in the list and it's saying, give me the total sum of all these. So here you see the cost of 0 is 49, 41 fuel, 37 fuel, 39, 41. And what we want to do is we want to find the minimum number. So what we're going to do is we are going to fold through our list, and each item in the list is going to be the position that we're looking for, as well as the total like movement cost. And what we're going to do is we're going to keep track of like the minimum so far. And the minimum is going to initially be nothing. And so what we want to do here, let me move this into a function so we can see what the types are here. This is going to be find minimum position. So this is, I think, the last function we need to write, which is find minimum position. And then find minimum position is going to take in a list of these, or it's going to take in one of these at a time. So it's going to say, we're going to take a position and a like a total cost. And what we want to do is take in the smallest cost we've seen so far, and we're going to return what the smallest cost should be. So basically, I think actually this should be, like this, because we're going to need to compare it to the previous cost position. Notice I've been saying basically a lot. It's not that basic. It's a little bit complicated. So if me saying basically is making you feel bad, I apologize. I don't notice that I'm accidentally saying things like that. So this is going to be like the smallest or the cheapest so far. The cheapest pair so far. So I'm going to do this and just kind of format this for a second. This is going to be the position and the cost. Let me format that. So what we're going to do is we're going to say, in the case where we found a cheaper pair, so if we found the existing position and the existing like cheapest cost, we can just, we can call this the cheapest cost. So far at least. And then what we're going to do is we're going to say if our cost is less than the cheapest cost so far, then we're going to return this as our new value. We're going to return the new, basically we're going to say our position and our cost is the lowest that we've seen. And if not, we're going to just return the position so far. We're not going to change what we found as the least expensive one. And then if it's nothing, we're always going to return ours. So basically, if we haven't found a cheaper position or cost yet and we get one, we're just going to automatically set that. So we should only see this the first time in the loop. So if I compile this, I think we're going to get two justs wrapped together. Oops. Cheapest pair so far. Boop. Oh yeah, and we don't need to wrap this in just because it's already a maybe. So that's what this is complaining about. It's like, hey, you're wrapping your maybe and another maybe. That's silly. Okay. So we're going to use maybe.and then. This helps like unwrap our justs in the output. And what we're getting is that 2, position 2, and then the cost of 37 is the cheapest. So we could have used a record for this to make it a little bit easier to read the output. But what I see here is that we've got the right value. So 37 fuel. How much fuel must they spend to align at that position? Okay, cool. So we're keeping the position, but we don't actually need to. So when I was doing this earlier, it turns out the position doesn't really matter. So we can simplify our thing. So this is going to be the maybe cheapest cost. It's going to simplify the code a little bit so that we're not looping through with a pair. And what we're going to do is we're only going to store the cost. If not, we're going to return the maybe cheapest cost. And this will make the code a little bit simpler. So we'll just get a number at the end. I was just discarding that extra position information. So what we're going to do now is we're going to get the puzzle input. Got a lot more numbers here. And what I'm going to try to do, let me add the type annotation back in. So it's going to give me maybe cost here. Okay. To cheapest fuel cost. Cheapest fuel cost. I'm just going to do that up here too. Cheapest fuel cost. Cool. All right, let me save this. In every video, I include these in the bottom in the description, so you can check out the code for part 1. There should be a link there. And it looks like we've got 344,605 for our answer. Let's see if that's right. Put this in our puzzle input. Hooray! 13 stars. Okay, cool. So I'm going to take this code snippet before I forget and put it over here. And that's part 1. So for part 2, we're going to basically just kind of tweak our code. There's usually like a little twist that they'll put on it. So let's see what the twist is for part 2. The crabs don't seem interested in your proposed solution. Perhaps you misunderstand crab engineering. As it turns out, crab submarine engines don't burn fuel at a constant rate. Instead, each change of 1 step in horizontal position costs 1 more unit of fuel than the last. And first step costs 1. The second step costs 2, and the third step costs 3. As each crab moves, moving further becomes more expensive. This changes the best horizontal position to align them all on. In the example above, this becomes 5. So Wow, okay. So things get more expensive because it's going to cost more, and basically our cost function is going to have to be swapped out. So it looks like with the old input, the answer is 168, and the position 2 is going to cost 206. So that's actually a good, that's good to know. So what we're going to do is we're going to make sure that we have the puzzle input from before. I'm going to just do this. We're back at 37. And what we need to do is we need to change our cost function to make it so that we're actually correctly calculating the costs. And then I think a lot of the body of what we've done here is correct. It's just going to be like some annoying math that we're going to have to do. So this is going to be to fuel cost. So what we had previously was a function that basically always just got the difference between the two, and that's how it got the fuel cost. So what we're going to do is we're going to take a position, and we are going to take like a single crab, and we're going to return an integer for that cost. So hopefully, target crab, our code won't change here. We can get rid of this lambda function that we had before. So with our previous solution, this was spitting out 37 for the cheapest thing. What we're going to do instead is we're going to change what this function does. But I think the rest of our code should be okay. So so what we can do is we can find the, so this is like the distance, which was just another number. And before, the fuel cost was actually just the same as the distance. But what we want to do is we want to make it so that each time you move like an inch, or move like move an inch, each time you move over a position, it's going to cost how far you were from the initial thing. So what I feel like we want to do is, if instead of doing this, I'm going to get rid of I'm going to get rid of this type annotation again, so that we can see what this returns. What we're going to do instead is we're going to make a list. Oops, so this is not an integer. I'm going to comment that out, comment this out. And then we can't do this tuple map stuff, so I'm going to comment that stuff out too. Oops, where's the tuple map happening? Here it is. So let's just kind of pick up where we left off here. Find the cheapest fuel cost. You find the cost of movement for a target position. Cool. And what's it complaining about? It's an end to a list of ends. Oh, this is right. The maybe.end then doesn't make sense anymore. Okay. So what this is doing, let's just take a look at the first one. So let's just grab the first item here. And we're going to go back to maybe and then for a sec. So this is what we're creating for this is going to be maybe.map. We're just going to grab the, actually, this is fine. So what this is doing is for each position, so like starting with if everyone moved to 0, these are going to be the costs associated with doing that for each member. So 16, for example, this is going to be a list of from 0 to 16. And we could do 1 to 16. I'm not sure what the idea is here. Oh yeah, so if it's already there, it's not going to move. So that's good. So this is this number is 0. So you can say like you can see what the position is. Start and then range. This will be an easier way to look at it. So if the starting position is 16, the range here that we're creating is 1 through 16. So what I want to do is I basically want to get these costs for each like distance. I think there's like a smart math way to do this where I don't have to like actually make lists. I have to like find like the I think I could just sum these costs up. I think if I did this and I just summed up these numbers, I think that would give us the cost that we expect here. So like here it's saying 16 would go 120. And it would basically do this for all of them. Give these names here. Target. So if the target's 0, these are the costs for each of the thing. And then basically what we can do is, I'll stop doing the list.head. So what we can do is we can like sum up these costs for each position. So what I want to do is so this is the cost for each individual one. Oops. The cheapest fuel cost. Oh yeah, and then this is gonna be a map. This is like for everything. This is kind of hard to read, huh? So let's take a look at a given target. So if the target was 0, all these have the fuel costs. So what we want to do is instead of having a list of costs, what we're going to do is we're going to basically just sum up the ranges. So we're going to do map, and then we're going to take the cost of each individual one, and this is going to be the cost here. And we're just going to want to get the numbers. And this will give us like all the costs for each, and then we can sum this up. So 241, if we go to 0, all these things. So let's quickly look at the puzzle and see. So it said if we went to position 5, it would cost 168. So I'm going to copy that and search for it in our output. So I'm not seeing 168 here. Okay, sorry, the distance minus 1 is what screwed me up. So by deleting that, it looks like the cost is corrected, is calculated correctly. And it said 2, to go to target 2, it now costs 206. Let's see if that's true. Okay, so it looks like our formula is right. What we need to do now, so let me clean up this code. This is starting to be a lot to read. We don't need to know about the starting positions. We can just calculate the fuel cost like we did before. So then this can go away. So we get the same output here. This tells us the target, but we don't really care about the target position. We just care about the sum. So what we can do is we can just say, give me all the costs of each of them. And then that would just give me a list of costs, and we don't have to worry about the position anymore. So I'm able to add that. Oops. List of costs, but the body is, oh, that's right. So this is the cost of, these are all the costs of movement. Whatever, we can keep list.sum in here, it doesn't really matter. So that is going to give us a single, so this is going to give us all those costs, and then for each one we're basically going to find the minimum. So this will be easier to write actually. List.map, or sorry, this is going to be list.minimum. So this is going to give us just 168, and again using and then here is going to unwrap those justs for us. So 168 was the answer when we use the test data. Let's see if when we use our puzzle input. So I'm going to save this real quick, copy that link. Hopefully it works and I can share it. But let's take a look at our puzzle input and see what we get if we paste that into our string. Ooh. Oh no. I have a feeling like it's going to be another browser crash problem, because we're basically generating lists for these crazy big numbers when really we could just be doing some math. Yep. Okay. Looks like it's going to be math time. So just like with part 6, doing it the naive way is not going to fly, and the reason for that is, oops, I think that's right. This is our code so far. The reason for that is because we're using list.range, and what list.range is doing is it's creating a list for everything. So if we had a crab move 500. That's creating 500 elements for each thing, that's a lot. And so when we're doing the cost of movement, we're doing a lot of work. So what we're gonna do, let me just keep these. So before we refactor, I'm gonna make sure that I have all my type signatures here, because this will save my butt when I get confused. Cool. So we have the right answer. What we need to do is we need to get the same answer, but we need to do it without enumerating like the minimum and maximum value in the list. So how can we do that? So I think minimum and maximum here was okay. I think this was the one that got us. Because if you remember from the last problem, we were using the min and max on our initial data set, and that seemed to be okay. So I don't think the performance problem's there. I think this is the performance problem. So what we want to do is, if we have a distance that needs to be traveled, there's some equation for this. So like let's just kind of like do it over here. So if we need to move 1, the cost is 1. If we need to move, if we need to move 2, the cost is 1 plus 2. You move 3, the cost is 1 plus 2 plus 3. And I think how this works out is if you double the number, how does it go? It's like 1 plus 2 plus 3 plus 4. So what's the sum of this? It's 1. What's the sum of this? It's 3. What's the sum of this? It's 6. I forget what the trick is for this. But if I wanted to sum up all these, I think I what is it? It's like you double the... I've done something like this before. Let's just keep going until we find more, until we find a pattern. Because I know it's essentially factorial, but for addition. And there's an equation for it. And we could Google it. Let's see if I can remember how to do it. It was like something about... These always add up to 6. It was like as you work your way in, this was the pattern, I think. This is the weirdest thing. I was on a road trip with my girlfriend to Minnesota, and for some reason this popped in my head, and we figured it out in the car. But basically what's happening, I think the mathematical pattern is if you take the 6 and the 1, you get 7, right? If you take the 5 and the 2, let me update these. 5 and the 2, you get 7. If you take the 3 and the 4, you get 7. So like if you take this number and you add 1 to it and you multiply it by half, so let me show you what I'm talking about. So we're going to take this number, we're going to add 1 to it. If it's even, you basically take the number, you multiply that by half of that number divided by 2. And I think this works. So if we did this, it would be 7 times 3, and you get 21, right? So that works. Let's try it with this even number. So we do 4 plus 1 times 4 divided by 2. That's 5 times 2, which is 10. Okay, let's see if the equation works for odds. I think there's something you have to do. I think you also add the other thing. So that didn't make sense what I said. But if we did this, it wouldn't work because we'd end up with a 5 divided by 2, and that would give us an integer. So, a fraction, not a whole number. So I think what you do here is you do this. So if it's 5 divided by 2, you round down. So this is going to be like the floor of that. And then you add whatever the middle number is. And so the middle number is always going to be 5 divided by 2. Or no, sorry, 6 divided by 2. So this is just 5 plus 1 divided by 2 again. So this is a trick. This is for odds, it's a little bit weirder. But let's take this and let's replace everywhere we see 5 with 3 and see if we get the same answer, right? So 3, 3, and 3. Oh, that's 35. Sorry. Okay, so 3 plus 1 is 4. If we divide 3 by 2. We get 1.5, but we're rounding that down. So that's just 1. So over here we have 4. So far over here we have 1. And then what we're going to do is we're going to add 2. So 4 times 1 plus 2 equals 6. So I think this works. And I think it works so much that I'm going to see if it works over here. So if we mod the distance by 2, and that equals 0, that means we're even. So I'm just going to kind of put that in a variable called isEven so we can see what that's all about. This is just using modulo arithmetic helps you get even numbers. So it's even if that's true. So what we're going to do is we're going to take our equation, we're going to take our distance, and we're going to replace those hard-coded values here with that. And we can do like the floor division like this. So just to give you a feeling of what I'm talking about, if I open up the Elm REPL and I do 1 divided by 2, it's going to give me 0.5. But if I do, so like if we do like 3 divided by 2, it'll give me 1.5. But if I do 3//2, that's integer division, and that's going to round down for us. So that's what we're going to do here, and that's going to replace the need to floor if we ever get into the position with the even number. And then here, what we're going to do is we don't have anything to add. So instead of doing this list range and then summing, what we're going to do is we're going to say if it's odd, we're going to do the same thing, but we're going to definitely add this at the end. Otherwise, we're going to lose that middle number. We don't want to lose the middle number. So we're going to take that same distance, do that, and we're going to divide that by 2. And so hopefully, I'm going to comment this out. Hopefully we still get 168 if I hit the compile button. So fingers crossed. Okay, I'm doing something. Mod by 2 is, oh, sorry, that's a Boolean. Just 168. Okay, cool. So that is the fancy pants math way of doing it. I'm sure there's some way I can simplify this fraction. I don't care. I'm pretty impressed that we were able to do this like on the fly, so we're just going to leave it like it is. And then I just want to make sure that 0 does what we want. So 1 times 0, that should work. So if we don't have to move, the distance is 0, the fuel cost should also be 0. So that feels good. Yeah, it was like a weird car ride where I was just like, hey, like, how do you do the factorials that way? Okay, so I'm going to paste that link there. So we have that, and then we're going to see if we crash our computer. I don't think we will this time. So we're going to run it, and this time we get a really big number, really fast though, so that's a good sign. So 93699985. Let's see if that's the correct number. All right, we did it. 1 solid week of advent code problems in Elm. I'm feeling pretty good about that. Okay, so both of those parts are going to be in the description below. I also have the playlist. If you're new to the series, you can check out. Mostly, it's just funny thumbnails. So I hope you've been enjoying them so far. But yeah, that's day 7. I am impressed with how far we've gotten through this because it's every day it's a crazy mind-bending problem. But we seem to come out okay on the other end, which is nice. In an hour, day 8 is going to be here. I will not be recording the video in an hour. I'll probably wait till tomorrow night to do that. But thank you so much for watching. If you have any questions, feel free to drop them in the comments below. If you like the video, like it. And I'll also have a link to the Elm Slack. If you want to reach out there and say hi, my tag is just @Ryan. And I also have like my Twitter and stuff down there. So yeah, thank you so much for watching, and catch you next time.